Dr. Huckabee here. This is a lecture from last semester, and it's a little weird because this is the first one where we start to mention coronavirus. So that was a weird one for me to see. Hopefully, it's a blast for the past for you, and you get a lot out of it. So without further ado, here is your to-do list. Oh, this lecture is also on Chapter 6 on kinetics and catalysis. So your to-do list is to do their homework assignment, which is due Friday, finish reading Chapter 6, and work the Chapter 6 problems.
What you need to do to stay healthy. Kind of brings us to things to think about before class. We have the meme, which might get funnier after the class, or if they're ever funny, they might be later. But a real live example of how organic chemistry can help you right now. You all had half a semester of Organic 1. You can understand now why people going to the grocery store and buying all the toilet paper and all the alcohol-based sanitizers don't make that much sense. Okay, the toilet paper, like that's a different thing. We won't touch that. But the alcohol-based sanitizers, while they say they kill 99.9% of germs, maybe 0.99, whatever it is not the best for specifically the coronavirus, which is a slight news article lately. The best thing for corona is what? You guys know? Have you heard the CDC recommendations? Washing your hands, yeah. For, what is it, like 20 seconds, a minute, something like that. Happy birthday. Okay, sing happy birthday, washing your hands with a good bit of soap, right? And there's a really good reason, an organic chemistry reason, why washing your hands with soap is so good with the coronavirus. Because the virus particle itself is covered in a lipid bimembrane. This is nonpolar. So, this means if somebody coughs a coronavirus and it lands onto some surface, like maybe metal or this, I don't even want to touch surfaces now, whatever it is, it's probably not going to have the same polarity as the coronavirus because metal is kind of polar, water is kind of polar, our lives are surrounded by kind of polar stuff. What's much less polar? Oils on your hand, stuff on your skin. So if you brush up against a surface that has that virus on it, it'll attach, just based on organic chemistry principles. But this is the beauty of soap. Soap, if you remember, has a partially positive part and a partially nonpolar part. Sorry, partially charged part in the head, and the tail region is nonpolar. And when you make a really nice soapy solution, you're able to bring all of that nonpolar stuff into the water with you, and then it goes right down the drain. The nice thing about coronavirus in the soap is that the soap will actually dissolve that bilayer membrane. And so the virus is completely inactivated, leaving you safe in that piece of skin at that time. So please remember your organic chemistry knowledge and stay healthy and wash your hands, I guess anytime you think of it, or if you feel like you might have touched something or surface, and keep them away from your face. Because the other thing about having a lipid bimembrane is if you think that you have a lot of oils on your hands, your face is worse, and parts that are moist all the time are even worse. So take the CDC recommendations fairly seriously, I would say, completely seriously. Yeah, so an actual real-world example. Okay, what we've talked about so far has been the reactants and the products, right? And figuring out if something is spontaneous. But that isn't super useful when you're talking about chemical reactions to only talk about is something spontaneous. Because there is no indication of how fast a reaction happens if you say it's spontaneous. The graphite in pencils that you might be using right now can be turned into diamond. Under the earth, extreme heats and pressures, right? That is actually a spontaneous reaction that could just happen one day, right? If you just looked at thermodynamics, you would say, all of this graphite in my pencil should be diamond, actually. It doesn't give you any idea of how fast a reaction might be occurring. And that's really what we're going to start talking about today, is what's called kinetics. And kinetics it sounds like movement, and it has to do with rates of reaction. And most simply put, the kinetics of a reaction are that the reaction rate is equal to a rate constant K times the concentration of reagents. So again, to do a little functional analysis here, the rate will increase when what happens? You have two things multiplied by each other. Rate increases when one of those other things increases too. 2 times 2 is 4, but 3 times 2 is 6. 3 times 6 is 18. The numbers get bigger, so the rate gets bigger. Does that make sense? Maybe? But this is a very vague reaction, or a very vague equation that doesn't give us the whole idea, because we're not looking at some random reagents. We want to talk about real reactions that might happen. So to get it a little less vague, let's imagine some reaction where A plus B goes to C. So now, in A plus B goes to C, so when A plus B goes to C, the rate law changes just a little bit, or the rate equation. Now it becomes the overall reaction rate is equal to, again, K, which is the reaction constant. However, now we have two different reagents, right? We have A plus B going to C. So now we have to account for both of them. And the most general way to do that is in this equation. Where you have A, the concentration of A times the concentration of B, and both have exponents that you could have, that could be there. And these exponents stand for how many of the molecule that you're talking about is needed to make the reaction occur, and if you just add all of the x's and all of the y's, so for instance, if x is 2, y is 0, you have an overall second order reaction. X plus y gives you the order. If you have overall zeros, then you have a 0th order reaction. And most commonly in organic chemistry, you'll see either 0, 1, or 0 first or second order reactions. There's a few listed on the board over there. And kind of magnify one of these. In a first order reaction, or sorry, in a 0th order reaction, the amount of material that is changed, so this reaction is stable. It just goes at the rate law, at the rate constant. That's the velocity or the kinetics of the reaction. So, in other words, let's say that, I don't know, you went out and had a very nice time on spring break, and you had 8 drinks, or you had 10 drinks, or 15 drinks. Your body is going to process all of that alcohol at the same rate. Nothing you do is going to make your liver work any faster. That's a 0 order reaction. 1 drink per hour, roughly, is about all our drinks can handle. First order reactions are actually tied to one of the reagents one of the reagent's concentrations, as you see here, rate constant times whatever A is, and that's just going to say as A gets bigger, that's much more quickly going to fall to 0, or whatever it is you're talking about. And then if you have second order, where it's the square of A, then it's going to drop off even faster. So that kinetics is obviously the most exciting subject that I could be telling you about right now. It's not dry at all. The problem with kinetics and talking about orders is that it is very math heavy for this class, something we're not going to deal with a lot. And it's, I don't know if you can tell, but that's differential equations that we're talking about, and we definitely won't be doing any calculus in this class. So really what we're going to be talking about in kinetics is instead what a reaction diagram might have to tell us in terms of kinetics. Because in organic chemistry, we're going to do a lot more with conceptual understanding and pictorial representations of these same exact things. So now, if we're going to talk about kinetics, we're going to be talking about a few different very important properties of a reaction. The first being activation energy, or energy of activation. This is essentially just how much energy it takes to get a reaction started, because it is the energy, the free energy or enthalpy between your reactants and the transition state, which is at the top there. The higher the activation energy, the less molecules actually have energy to do the reaction. Okay, it's 5:30. We're right on schedule. Very good. So let's say you know how much energy it takes to get the reaction started, but you also know your molecules are only at this energy. You could kind of think about this same exact process. Whoa, I gotta be careful. Sorry. Ooh, okay. I'll try and keep my head in the same place. So if the molecules don't have enough thermal energy to get over that wall, you know, it's going to be like a lot of this. They try really hard, but they're never going to get there, right? If instead you can increase that energy of your molecule, perhaps by raising the temperature, then what you'll have is a much better scenario. Your molecules can make it over the wall, and you'll actually have your products at the end of your reaction. Which brings me to a good point. Temperature is energy. Do you remember from your Gen Chem class or maybe your beginning physics class? Temperature is heat, heat is energy, all obeying the thermodynamic laws. If we add energy to the system through temperature, this is exactly what we're doing. We're raising the energy of our molecules up so that the energy required to do the reaction is less. Okay, so that's two things. So we talked about activation energy, and we talked about temperature, and that's two big important parts of kinetics. However, what we didn't talk about is something that's a lot harder to quantify. The third thing, the final thing in this like broad overview of things we care about in kinetics, is very important in organic chemistry, and it leads me to ask you all a question. How often have you ever taken a bus or subway? Raise your hand if you've taken any public transportation. Oh, good, look at that. Yeah, I love seeing it. Okay, so you've taken public transportation. Has it ever been really crowded? And it's just like, you get on, but you hate it, and you have to stand or sit next to people you wouldn't want to normally. This is the idea of sterics. In your mind, you getting onto that transportation is a lot harder, your energy of activation is a lot higher whenever there's too many people inside that vehicle, right? You say, oh, this sucks. That is the idea of sterics. Molecules can also be very big. If the center that you want to do a reaction at is kind of like clustered, is kind of like this very overcrowded bus or train, the molecule you're reacting it with is going to have a lot higher activation energy because it's going to be a lot less happy about getting on the train, right? So sterics is something that we're going to talk about throughout the class. A lot more when we get into reactions because sterics controls a lot of kinetic outcomes. Okay, so I'm fully aware that this has been a less interactive part of the lecture so far. So what I want to do is keep our talk about kinetics alive, thinking about this wall. And instead, I want to take you somewhere, and that is Switzerland. Maybe you guys have seen Sound of Music or something. That is in the eastern part of Switzerland, where they meet with Austria. I'm going to talk about the southwest part of Switzerland, where they border France and Italy. Because it wasn't so long ago that these huge mountains, it's such a shame that these slides aren't in both places. I'm sorry about that. These huge mountains had to be physically traversed to get from one side of the range to the other. This region, the southwest Switzerland region, see if I have I should have included it. No, I didn't include a map. That would have been smart. Anyway, so in the southwest of Switzerland, there's this region called Valais, which is essentially one giant valley. And farmers in Valais were very successful growing livestock. And so what they would do is they would start in this town, or near this town, called Leukerbad, and they would climb all the way up the mountain with all their sheep, cross a dangerous path, a pass through the mountains. I'm going to use the mouse. Maybe there's a laser pointer. That's so good. Okay. They would cross this pass here from Leukerbad all the way to Kandersteg on the other side. And this would take days with their giant herd of sheep, right? This is a huge amount of energy these people are having to put in, all for what? To get to a market on the other side in Kandersteg so they can sell their sheep. This was maybe 150 years ago, not even 150 years ago, you know. Kinetics is all about what we're going to talk about here. Catalysis is kind of like the modernization of our society. In the old days, it took so much energy just to get over the mountain and sell your sheep. But now, what if instead of going over the mountain, we took the Swiss approach? Has anybody played the game Trains? Ticket to Ride. It's a board game. It's like, I don't know, if you don't like board games, it's fine. But Switzerland is really famous for its train tunnels. So what if we built a tunnel through this mountain of activation energy and came out on the other side into Kandersteg by train? That's essentially what a catalyst does. A catalyst takes a reaction profile that looks just absolutely disparaging. Here's your reactants, here's your products. Just a mountain of an activation energy to get over. You know your product, your reaction should be spontaneous, but the activation energy is just way too high, right? This is your activation energy. It's way higher than the energy gain you get from going from reactants to products. So a catalyst does the reaction a little easier. And so now you have to put in a lot less energy and you still get your sheep to market. All right, so you can be honest with me. Was that story boring? I'll give you a better reason to care about catalysis. You cannot ferment sugars to alcohol without catalysts. Right? So without yeast, which is a good catalyst for fermentation, you wouldn't have wine, you wouldn't have beer, and you wouldn't have bourbon, which you guys know comes from Kentucky, obviously. But the other two things are Swiss. So Switzerland also has grapes that they grow on the side of the mountain, and they can make beer as well. Just fun little facts. Yeah, so beer is important, and that's why we care. Okay, so we talked about how to read this stuff. We had a fun little diatribe into Europe. But what we really want to know is, can we use what we just talked about directly in a reaction diagram? Because that's way more important than burping. If you, during your studies for the last exam, you encountered this, this question from the last, I don't know, F9, it was like exam 2, F19, something like that. You saw this reaction diagram here. And while you could not have answered it then, you already know almost everything you need to know to fill in every single one of these blanks. We'll just start together. We know from thermodynamics what 1 and 5 are, right? That's pretty obvious. That's what? Reactants and products? Do you guys remember what E is? Another thermodynamic thing we talked about? Yeah, the change in free energy, exactly. Do you know what, let's see, go across. What about D? Do you know what D is now? I think it's something we talked about in kinetics. This is the activation energy, right? All right, that's good. So we're getting close to having almost everything. What about C? Do you know what C is? Ah, it's a tricky one. It's also an activation energy, is it not? That one's tricky because we haven't explicitly talked about 3 yet, but you can see that C is just a difference in energy between 3 and its energy of activation. Or the peak there. Right. So then really, the only things that we can't answer at this point are what 2, 3, and 4 are. Am I missing something? Do you guys agree with me there? I think we know everything else otherwise. Two, 3, and 4, well, 2 and 4 together are both what are called transition states. We'll talk about it in a second. I'm going to leave this slide up as we go through some other things. Those are called transition states, and 3 is called an intermediate state. You can remember it if you remember that transition states are peaks and intermediates are valleys. And those things are separate from your reactants and your products. Because remember, you always find those things first. You say, oh, that's my reactant, because that's where this thing starts, and the products are where this thing stops. So you're looking at peaks and valleys. So now you can see a pretty difficult reaction diagram, and you can know all the things about it. But I have a question to pose to you all. These have all been fairly straightforward, and have only involved, one reactant going to one product. But what about if I told you that it's not always that easy?